First of all, thanks to Jay and Wolfram for the invitation. It's been very inspiring so far already. I'm happy to talk about our work on engineered heart tissue transplantation, but then also try to include some newer data. And I would like to start with the pathophysiological problem that you can see here. Myocardial infarction leads to an irreversible loss of myocytes. And our current pharmacological strategy, beta blockers, ACE inhibitors, mineralocorticoid receptor antagonists, and more recently sodium glucose transport inhibitors, are not able to address this major underlying problem, the loss of myocytes. And we've heard many strategies already, and ours is similar, that aims for something that is conceptually very different, that aims for remuscularization. And I think there's a rationale for this strategy. If we look at the correlation between infarct size and left ventricular function, we see that there's a negative correlation between infarct size and ejection fraction. And this has been shown in rats. And even though there's not too much data in humans, there are studies that also demonstrate a negative correlation between infarct size and ejection fraction. The larger the infarct, the lower the left ventricular function. And obviously, you might say this is not surprising, but I would like to highlight one point. Let's look at a patient with a myocardial infarction that affected 50% of the ventricle. We then aim for remuscularization, thereby decreasing infarct size, and hypothesize that this will result in an improvement of left ventricular function. And if this hypothesis holds true, this is what we're supposed to see. But the point that I would like to highlight is that we need a substantial remuscularization to achieve a meaningful functional benefit. So we wanted to address how many cells do we have to transplant to achieve this functional benefit, and for this we performed a dose-finding study in guinea pigs, which is also our favorite model. We performed a cryo injury and then transplanted engineered heart tissue patches and followed these animals over time. We included 4 different groups: a control group that received cell-free patches, a low-dose group in which we transplanted engineered heart tissue patches with 3 million cells, a second dose in which we transplanted 6 million cells, and then a high-dose group in which we transplanted patches that contained 12 million cells. So what were the morphological consequences? Well, obviously, no human cells in the cell-free group. Most of the cells in which most of the hearts in which we transplanted 3 million cells did not contain any human cells at all after 4 weeks. But the ones that did contain human cells showed only very small grafts, shown here. There were slightly larger grafts in the dose 2 study group. On average, this was 5% of the scar. And only in the high-dose group, we were able to remuscularize a substantial part of the heart, and on average, this was about 13% of the scar. So what were the functional consequences? And for this, we performed echocardiography, a baseline echocardiography, a second echocardiography prior to transplantation, and a third echocardiography after 4 weeks. And you can see the 4 different groups here. This is shown here in white, the cell-free group. In this light red, the dose 1 with the 3 million cells, and then here in the dark red, the dose 3, the high-dose group in which we transplanted 12 million cells. And it was a similar drop in function after injury in all those groups. Transplanting cell-free patches did not improve left ventricular function, but also transplanting patches that contained 3 or 6 million cells did not improve left ventricular function. And only the high-dose group resulted in an improvement of left ventricular function, further indicating that we really need to remuscularize a substantial part. So it's the myocardium that matters. And then this all goes back to the hypothesis that these transplanted cells, the engrafted cells, actively participate in left ventricular function. And even though this is all indirect evidence, this question has never been addressed, and I will talk about this in the second part of my talk. But what does it mean for a clinical translation? Well, obviously we don't want to treat guinea pigs. So a guinea pig heart is about 2.5 grams. And we needed at least 12 million cells to see a functional benefit. Well, if we assume a linear relation and say the human heart weight is 300 grams, we end up with 1.5 billion cardiomyocytes that we need to transplant in the engineered heart tissue approach. Is this feasible? Well, it's difficult, but I think we're on a good track here. We scaled up the engineered heart tissue patches from this medium-sized version that contained 12 million cells to a human-scale patch, 5 to 7 centimeters in size, containing 450 million cells. And just like the smaller counterparts, these coherently start to beat in culture. And in a proof-of-concept study, we transplanted those epicardially on pig hearts. But do these cells really actively contribute to left ventricular function? And to address this question, we set up a study in which we said, well, okay, we have an animal model that has a baseline left ventricular function. We injure the heart. This will result in a drop of left ventricular function. We then transplant the cells, which will partially remuscularize the heart, thereby improve left ventricular function. And we now engineer the cells in a way that we can selectively switch off contractility in the engrafted cells. So, and then we assumed, okay, if we selectively switch off cardiomyocyte contractility, if the cells actively participate, we expected to see a drop in left ventricular function. And then when we switch on contractility, again, we expected that left ventricular function will resume to baseline. Whereas if they do not actively contribute to left ventricular function, neither the off nor the on switch should affect left ventricular function. And for this, we created iPS cell lines with something that we call off-on switch, and by now we have several of these lines, and for today's talk I would like to focus on an optogenetic version in which we knocked in a so-called inhibitory luminopsin that consists of an anion channel that can be activated via light. This is eye clock, but also a luciferase that can be activated via the luciferase substrate coalanteracine and then thereby opens the channel. And we hypothesized that by electrically inactivating the cardiomyocytes, we will reversibly stop cardiomyocyte contractility. And then we generated engineered heart tissue for functional characterization, and in the upper row you see a wild-type engineered heart tissue, and this is an original recording. These are the individual contraction peaks. Photostimulation did not affect wild-type engineered heart tissue, and when we electrically pace them, 2 Hertz frequency increases. In contrast, if we do the very same thing with the ILMO EHTs, you see them beating. Photostimulation leads to an immediate stop of contractility, it's shown here. The EHTs are not excitable during that time, and when we stop the photostimulation, it takes a few seconds, and then contractility starts again. So we then went on and transplanted those cells in the guinea pig model, and this is ongoing work, and I can only talk about one part of the study. And in this part, we did not transplant engineered heart tissue patches, but directly injected the cell into the injured heart 1 week after injury, and then we followed the animals over 4 weeks, and that's one of the examples. And you see the scar here and the partial remuscularization, that's the YFP positive cells, you get this whitish staining. And very similar to the previous study, on average, we remuscularized about 15% of the scar. We then went on and did Langendorf analysis to assess left ventricular function. This is shown here. and performed a photostimulation either with blue light to activate the channel and thereby stop contractility selectively in the engrafted cardiomyocytes, or as an internal control, performed photostimulation with red light that does not activate the channel. And this is the result. Photostimulation with blue light resulted in an immediate drop of left ventricular function here. And after termination of photostimulation, left ventricular function resumed to baseline after a few seconds. In contrast, if we performed photostimulation with red light, nothing happens at all. And then I would like to have a closer look at this and these parts here. And this is the quantification for all animals. Photostimulation with blue light led to a small but significant drop in left ventricular function that completely resumes to baseline after the termination. And very similar to the in vitro data, this takes a few seconds. In contrast, red light has no impact on left ventricular function. So if we look at the individual animals, we see that only a subset, about 50%, slightly more than 50% of the hearts reacted to photostimulation. So some of them showed no effect, and the other 50% showed a drop in left ventricular function. So what was the difference between those two groups? And that was the main difference. Main difference was graft size. Graft size was substantially larger in the hearts that showed a drop in left ventricular function than in the hearts that did not. So to sum it up, we think that we provide evidence that engrafted cardiomyocytes can actively participate in left ventricular function, which is conceptually very different than all our current therapeutic strategies. We believe that graft size is an important, probably the most important determinant for the functional benefit. And when we look at our engineered heart tissue dose finding study, and assume a linear relation, we come up with a number of 1.5 billion cardiomyocytes that are needed for this strategy for our model, the engineered heart tissue transplantation. With this, I would like to thank you for your attention. I would like to thank the group in Hamburg, and I would like to thank our collaboration partners in Munich for the large animal work. Thank you.
Good talk, Florian.